So the first topic we look at in Year 12 Chemistry is called Metals in the Reactivity series. It's quite a good topic to start with because it uses a lot of the skills you've looked at in Year 11 Chemistry. So in this topic there's going to be a lot of reactions, a lot of observations and a lot of chemical equations. So all those skills you built up last year you'll find very helpful in this topic. To give you a wee bit of an overview about what the topic's about, it's clearly about two things just looking at the title. So it's about metals and how they react, and also the reactivity series. Now metals first, we have actually looked a fair bit last year about some reactions of metals. We looked at metals reacting with acids to make a salt plus hydrogen. We also looked at the reaction of the group 1 metals with cold water. But we're just doing a wee bit more detail about those reactions in this topic. To give you a wee bit of an overview where we're going with this. With the reactions we'll look at, we've looked at some of these before. We're going to explore the reaction of metals with oxygen and also with cold water for all of them, and also with steam, which is hot water. So we've got a couple of new reactions as well. We'll also look at a type of reaction called a displacement reaction. The second part of this topic is about the reactivity series, which hopefully you might remember from junior school, year 9, year 10. All the reactivity series is trying to put chemicals in an order of reactivity, so from most reactive down to least reactive. So we're doing that with the metals here. What we're going to get to, so it's helpful to show you right at the start, is putting a set of metals in order of reactivity. So obviously there's loads of metals, but we only pick 8 for this topic. So potassium, sodium, calcium, magnesium, aluminium, zinc, iron and copper. What we're trying to do is put them in an order from most reactive, which is potassium, down to least reactive, which is copper, and how we justify that. How we are going to work it out, as we'll see in the rest of this booklet, is by studying the reactions and trying to work out a pattern about which reactions tend to be most vigorous and which reactions tend to be least vigorous. So to put it all together, what this topic's basically about is some reactions of metals and the observations and equations for those reactions, and also how we use those reactions to put these metals in an order of reactivity from most reactive down to least reactive. So that's what the topic's about. So what we're going to start with is our first reaction we have to look at, which is the reaction with air. More specifically, air, the reactive part is oxygen, so you could also describe this just as the reaction of metals with oxygen. So that's a new reaction. We haven't really looked at that last year. So we've got a general equation to work out what's going on there. When you react a metal with oxygen, you make one thing. It's called a metal oxide. So it's a metal oxide, that's a metal and a non-metal. It's an ionic compound. So we'll look at the reaction. Let's look actually the practical part of it. Now obviously if we were in school I'd literally be showing this reaction to you in front of you, so you just have to go with my description for now. For a lot of these metals, what you can do is just kind of hold the metals in a Bunsen burner flame and just see what happens. It's not perfect for all of them, it's not the proper scientific way of doing it, because lots of the metals might melt and drip onto the table, might be a bit too reactive. So the proper scientific way to carry out the reaction of a metal with oxygen is this setup here, and this is what you should draw on the exam if they ask for a diagram for this point. You'll put your metal in the crucible, so that means if it melts it doesn't go anywhere, it's just kind of held in a wee cooking pot there. You have a lid on top and that allows some of the heat to be trapped to get hot enough for the reaction to take place. You've got a Bunsen burner underneath, obviously providing the heat because some of them take a wee bit of effort to get them to react, and your tripod and biped triangle just to hold everything together. One wee practical point, potassium, sodium and calcium, which are top of a reactivity series, as we'll see in a second, we don't normally do that in school, so we wouldn't do this setup with those three metals, just they're a bit too reactive. It's a bit dangerous to do it in a school lab. However, all of the other metals can be heated quite easily with a setup, and you can observe what happens after the reaction. One wee practical point which often gets asked in questions, there is an obvious problem with this setup if you think about it. So we said use the crucible because you want to hold the metal in. You use the lid on top because you want to get nice and hot, a bit like putting a lid in a saucepan. But if you think about it, the metals try and react with oxygen, but you've got a sealed container here. So there is some oxygen in there above the metal, but it's going to be used up quite quickly, and then you've got no oxygen to continue the reaction. So what you're meant to do as you do this reaction is to lift the lid up just with some tongs, just lift it up, put it back down. That lets a little bit more air and oxygen into the crucible to keep the reaction going. So you can lift this on and off as you proceed the reaction. So that's the equation in general. Here's the practical points for it. Now let's look at the observations for them. So as you see in this table, you can react all these metals with oxygen. We hinted at the fact you wouldn't probably do these three in the school lab, but they do obviously react. and they've all got a different observation, so from potassium down to copper. One kind of general point is, we said this is an order of reactivity. These three are very vigorous, you get flames very quickly and they react quite quickly. Once you get down to copper, it's not actually burning with the flame, it's just kind of going black. So you've got a spectrum going down in observations from very vigorous observations to not very vigorous observations, which helps us put them in order. So in terms of what you need to know, first thing is, unfortunately, is a wee bit of kind of rote learning, which is a bit unfortunate. You are expected to know these observations off by heart. Now obviously you can read, but I'll just go through them quickly. Potassium's distinctive observation is that it burns with a lilac flame. You've seen that before in other reactions. Sodium burns with a yellow flame. The way I always remember that is that street lights actually contain sodium metal, and that's why they have that kind of yellowy orange colour. So I remember sodium always is yellow. Calcium burns with a red flame. Magnesium burns with a bright white light. Hopefully you remember that one. You've seen that plenty of times, that experiment. And you get a white solid at the end, as with the other three. Aluminium, it's very boring. It only burns when a fine powder. It won't actually burn when you put a lump of aluminium in. You have to grind it up. But again, just burns to make a white solid. Zinc, a little bit interesting. It's going to make a powder. But interestingly, when that powder, the zinc oxide, is hot, it looks yellow. It actually changes colour when it cools down. It goes back to being white. Iron, if you burn filings of it, it'll get orange sparks. That's actually the observation. You write down orange sparks and you form a black solid. And copper, as I mentioned, it's the least reactive. You're not going to get much of a flame or anything too vigorous. It's just going to gradually turn black. You get a black layer on top of the copper, which is copper oxide. So, filling in the equations then, so as I said, you just have to learn those observations off and for today. Just giving you the symbols as well here. So potassium, sodium, calcium, magnesium, aluminium, zinc, iron, and copper. So what we could be asked to do, and you could get for any one of these 8 reactions, is to give a balanced symbol equation for the reactions. I'm going to do the first one as an example, but I'll probably try and get you to pause the video and have a go at the rest yourself, because it's good practice on the skill you looked at earlier on this year. So if we look at our general equation, we know it's potassium plus oxygen goes to potassium oxide in this case. So if you're struggling, it's always a good idea to give the word equation first. But again, once you get a bit more proficient, you can just go straight to the symbol equation. So I'm going to substitute all these words into symbols. Potassium, just the metal, is K. Oxygen is O, but I have to remember it's diatomic, so I have to write O2. Then potassium oxide, now this is just a ionic compound. Potassium is a metal, oxygen is a non-metal. So to get its formula, I just need to do a swap and drop. So if I look at my periodic table, which you might need, potassium's in group 1, it's going to be K+. Oxygen's in group 6, so it's going to be 2-. If I swap and drop that, I get K2O. Almost there, just need to make sure it's balanced. Not actually the easiest one to balance necessarily. I probably would start with the oxygens first. There's 2 here, but 1 over here. So put a big 2 in front of this. That actually gives me 4 potassiums. So I need to get a 4 in front of here. So hopefully that jogs your memory about how you do these kind of equations. See if you can have a go at the rest of them now. Just before you do, iron's a little bit of an unusual one, so maybe skip it. I'm going to explain that in a second. So hopefully I haven't had a go with them. I'm just going to write down the complete equations, make sure you've got them correct. Sodium's also in group 1, so actually has a very similar equation to potassium. It's going to have similar balancing and formula. Calcium is in group 2, so it changes slightly, so you get 2Ca plus O2 goes to 2CaO, because 2 plus 2 minus swaps and drops cancels out. Magnesium is going to be very much similar to calcium. 2Mg plus O2 goes to 2MgO. Aluminium, probably a hard one, it's in group 3. What you end up with is aluminium reacts with oxygen. The swap and drop of aluminium oxide is Al2O3. To balance it out, I need to double up my aluminium oxides. That gets 6 oxygens here to match with 6 oxygens here. 4 aluminiums here, 4 aluminiums need to be on this side as well. Zinc, it's in the back of your periodic table, it's zinc 2+, whenever it forms a compound. So 2Zn plus O2 goes to 2ZnO. Now, iron is very much the unusual one. The problem with iron is, if you have a periodic table, look at the back of it, you'll see that there's two different types of iron ion, Fe2 plus, Fe3 plus, which obviously makes it a bit tricky if you're trying to get the formula of iron oxide because you're not sure which one you're meant to use. The reality of what happens is, I'll just grab a bit of paper here to show you, is this. You actually get two simultaneous reactions going on here. Iron reacts with oxygen, and in this case you might get Fe2 plus forming with the oxygen. That would swap and drop to get FeO. That's one potential reaction. To balance it out, you would just put a 2 here and a 2 here. But the other alternative reaction is you can react to get iron oxide with a 3 plus charge. So in other words, Fe3 plus O2 minus, a little bit like aluminium oxide, which ends up with Fe2O3. Balancing it out, you need a 2 here, a 3 here, and a 4 here. So that's a bit of a problem. You've got two potential reactions, but you might have to give like one reaction. The kind of solution we come up with is we kind of average out these two potential compounds we get. Imagine it's kind of 50-50 of each. If it's 50-50 of each, we kind of add them together, which in other words would be 3 irons and 4 oxygens. It sounds a bit made up, but it is actually the way we do it. So if you're asked for the reaction of iron with oxygen, you're aiming for Fe3O4, even though it's actually what that actually means is just a mix of FeO and Fe2O3. The rest of the equation just have to balance it, so it's going to be Fe plus O2. So you need 2O2 and 3 Fe. Don't worry if you didn't fully follow that. Essentially, you might just have to learn this equation off for the iron one. Seems quite tricky. It's never actually come up in the exam yet, but they would be allowed to ask that to you. So filling that in for you, it's going to be 3 Fe plus 2O2 goes to Fe3O4. Copper, finally, it's another one in the back of your periodic table, so to get its charge, you just look it up, so it's Cu2 plus in the compound, so it goes to 2Cu plus O2 goes to 2CuO. Okay, so in that first page, first reaction, we've got some observations that to learn off by heart. We have to appreciate that potassium is most reactive and then gradually getting less reactive down to copper, and you could be asked for a balanced symbol or word equation for any one of these reactions in the exam.